Internet of Things in cyber physical systems, and we have 5 talks from experts in the field talking about attacks and defenses, about industrial IoT and cyber physical systems, ranging from attacks in programmable logic controllers and in industrial control systems, water distribution networks, and power systems. The first presenter is Dimitris Dihalas from New York University, and he will talk about potentially leaky controller, examining the cache side channel attacks in programmable logic controllers. And with that, I will mute myself and project his presentation, and then we'll follow up with Q&A.
My name is Dimitris Dihalas, and I'm a PhD student at NYU Tandon School of Engineering, and I would like to present you our work named Potentially Leaky Controller, Examining Cache Side Channel Attacks in Programmable Logic Controllers. At this point, I would like to acknowledge my co-author, Michalis Maniatakos. Industrial control systems are the core of modern industrial automation. They are small computers implementing simple control logic to drive industrial machinery. In the last decade, however, ICS are migrating towards the industrial Internet of Things, following the paradigm shift of Industry 4.0, meaning that ICS are becoming small, interconnected and decentralized devices that are being based on open platforms such as embedded Linux, for example. At the same time frame, side channel attacks have been identified as a very potent threat in any kind of computer system. They are highly stealthy confidentiality threats that can be leveraged to exfiltrate information from any type of system through some indirect way, for example, power, sound, light, or time, the so-called side channel, and they can affect a wide range of devices. One particular category of side channel attacks are the cache side channel attacks or timing side channel attacks. Now, this has been used to build covert communication channels through the cache by leveraging the different the access times between the cache and the main memory. In the Spectre attacks in 2018, the authors have showcased that by also exploiting a vulnerable architectural feature to execute illegal instruction in conjunction with the covert communication channel, an attacker can exfiltrate information from any vulnerable application or any kind of vulnerable software at the application level. And now, let's talk a little bit about the PLC, the Programmable Logic Controller, which is a very prominent industrial control system. It's a small computer implementing control logic. For example, if temperature rises beyond a certain threshold, move a robotic arm or close a valve or something similar. Now, this control functionality in modern PLCs can be abstracted to software application level through some platform such as the Codesys platform. Now, this platform also handles all logic functionality and communication, such as network and I/O, and this introduces the vulnerability in modern PLCs. Since everything is abstracted as an application, cache side channel attacks can be leveraged to exfiltrate information from the PLC. Now, let's take a look at the different levels of the PLC that can be exploited to exfiltrate information. First is the I/O, the input and output. In PLCs, input and output is handled by dedicated hardware called I/O modules that can be connected wired or wirelessly. Now, these I/O modules are interfaced to the PLC through the dev subsystem, a driver subsystem, which is a piece of software that is vulnerable, that is a vulnerable point through some kind of attack like the evict and reload, and can be used to exfiltrate process data. The next is the system level. Now, the main framework Codesys runs as a root process, which makes it at the same level as the system, which can be leveraged to exfiltrate information from the system itself, information such as cryptographic secrets, such as the shadow file. Next, let's check the network level. More specifically, Modbus. Modbus is a main protocol for data transmission. It's the most popular in industrial control system. It connects the PLC to a remote human-machine interface, or HMI. And it's implemented in software and executed as a thread on the PLC, which again, since it's at the application level, it's susceptible to Spectre type of attacks. It's a vulnerable point to exfiltrate process data, since sensors and actuator data are being communicated through the Modbus. The next is the OPC Unified Architecture, or OPCUA, which is a machine-to-machine communication protocol. Now, this protocol offers development and debugging capabilities to the process engineer, which means that it transports sensor and actuator values to and from the PLC, which makes it a vulnerable point for process data exfiltration through Spectre type of attacks. It also utilizes encryption for the in-transit data, storing encryption keys in its own memory space, which also makes it a target for exfiltration of cryptographic secrets. Now let's check the application level. The control application is implemented as a typical software application, as a program, as a binary that runs on the PLC. Now, this control application specifically has a static I/O memory mapping in the application memory space, which means that an attacker can directly target this memory map, this memory space, to exfiltrate process data information from the application cell, since again it's an application level vulnerable to Spectre type of attacks. And finally, we have the K-bus, which is an inter-process communication protocol. It handles information exchange between different processes or threads of the same process. It's been utilized to carry I/O data from the I/O module device to the control application itself, which again, since it's a piece of software, it's a thread, it's an application, it makes it vulnerable to Spectre type of attacks that can be leveraged to exfiltrate process data. Thank you very much. Let me know if you have any questions.
Thank you, Dimitri, for the pre-recorded presentation and for the interesting talk. Does anybody have any questions? I don't see any questions at the chat. Maybe somebody has any questions he or she would like to ask Dimitris Stichalas. If not, let me ask you a few questions, Dimitri. So what defense strategies can be employed to protect against these cached side channel attacks in programmable logic controllers? So what are the protection mechanisms in place to protect such types of against such type of attacks?
Hi, Harry. Can you hear me?
Yes, we can hear you.
Thank you for the presentation. So the main enabler of this type of attacks is architectural features, which means that ideally, in order to protect against this kind of attacks, the measures must be taken at a micro architectural level, which means that the processors essentially must be redesigned. But on a more practical approach for the devices that are already implemented, since PLCs focus more on robustness and reliability rather than performance, for example, there are many ways that the PLCs can be protected from confidentiality attacks, such as Spectre, for example, which is using, for example, disabling entirely disabling speculative execution, which is the main enabler for Spectre, or wiping the cache after every context switch, which is something that in normal computer systems it cannot be done. It will degrade performance very much. But in programmable logic controllers, which are more focused on reliability, that won't be that much of a problem. Also, there's the notion of cache warming, which is filling the cache with information which can lower the accuracy of these type of attacks, which is again something that a measure that degrades performance but makes this execution much more reliable in terms of confidentiality attacks and leaking information.
Okay, thank you. I have also actually a follow-up. If anybody else has any questions, please interrupt and ask Dimitris. I have a follow-up on that. So in terms of the attack perspective that you try to explain, so how is it possible this kind of Spectre type of attack can be delivered to a PLC? So
the threat model is actually not that strong, because Spectre type of attacks are user level attacks. So the main assumption is that the attacker must have access to the PLC, remote access to the PLC, user level remote access to the PLC. In our research, we have used the Shodan platform to search for PLCs with Codesys framework, which uses a very distinct IP port. And you will be very surprised to see many PLCs are connected to the internet, not some closed down network, industrial network. And the thing is that many of these PLCs still retain the same login credentials that they came up with, which are known to the public. You can essentially log into the PLC and launch an attack from there as a user level program.
I see.
And this is something very easily done. It doesn't need much technical expertise. If for example the attack vector is being handed to you because Spectre code is available online, is the proof of concept is online, right? So
I see. Yeah, I think. Thank you. And there are more questions in the Slack. I think we have time for questions since your presentation was a bit short. One is asked. You mentioned that Modbus is as a potential entry point for attacks, right? So have you studied other communication protocols? That is the first part of the question. And the other part of his question, are there any countermeasures on the protocol side?
So we actually, our main focus on PLCs is more on the application and system level. Network is being generally covered by thoroughly covered by research. It's the first line of defense when coming to pretty much any computer system, right? We have the only protocols that we have focused is the Modbus and the OPCUA that we presented. Now, countermeasures on the protocol side, the first level of defense again in terms of confidentiality attack is encryption, right? And OPCUA enables encryption for secure communications, but the problem with these implementations is that they also run on an application level in the PLC side, right, where they are susceptible to this type of attacks. So in order to secure any communication, you also have to secure to isolate the memory space of the communication threads. For example, you have an instance of the Modbus protocol as a software application, which is not isolated with some kind of sandbox, for example, right? And while the communication is encrypted, the cryptographic secrets are in plain text in the application side, in the application memory, which shouldn't be able to be accessed, but through Spectre attacks it can be. So on that level, isolating, providing some kind of isolation in the application level for the communication protocols is the way to secure this type of attacks, against this type of attacks.
Thank you, Dimitri.
Thank you for the questions.
Any other question? I think we may have 1 minute for another question, if anybody wants to have another question. So maybe I ask you one simple question. What percentage of these PLCs that are out there in Shodan, you mentioned Shodan, are affected by this type of attacks? Do you have any number based on your experience?
So the only number that we can approximate, we don't even have, is the amount of devices that have enabled, that the Codesys platform enabled, but that we don't know if they have the same software. So we can conservatively say that the amount of internet devices, right, that are connected to Shodan in terms of share of the PLCs are around 10 to 15% of the available devices through internet. So we can approximate that, right? But we haven't actually checked if they still retain the same credentials. We haven't tried to log in because it will be a bit sketchy if we did so, right?
Okay, yeah, I see. So it would be sketchy. Okay, thank you, Dimitri. Thank you for the nice presentation.
Thank you very much, Harry.
So the next presentation, pre-recorded presentation, is by Solon Falas. and he will talk about his work on physics-informed neural networks for securing water distribution cyber physical systems. And with that, let me go to this presentation, mute myself and play the pre-recorded presentation of Solon.
Hello and welcome. In this presentation, we are going to talk about an emerging deep learning framework called physics-informed neural networks and how it can be utilized to secure water distribution systems under specific cyber attack scenarios. The other co-authors in this work are Haralambos Konstantinou and Maria Michail. In recent years, we see the physical world blend with the cyber one in an effort to create fully automated physical processes in different aspects of our lives. The cyber environment monitors and controls the behavior of the physical system based on informed decision-making mechanisms through feedback loops, usually comprised of a variety of sensors and actuators. Examples of CPSs include water management and distribution systems, power grids, and industrial manufacturing systems. The security of CPSs, such as those deployed in critical infrastructures, is of crucial importance due to the catastrophic consequences that may occur in case of system failures. Embedded systems for CPS monitoring and control, spanning over large areas, are likely to be controlled over wireless networks, which makes them an alluring target for cyber attacks. Recent cyber attacks on CPS infrastructure portray the prevalence and importance of such incidents. For example, on April 24, 2020, an event was reported by Israeli officials stating that the cyber attack aimed at disrupting water supplies by increasing chlorine levels in drinking water. Cyber-physical systems are usually created using the following setup. A physical process is monitored through various sensors, recording different metrics in different locations in the system. For our example regarding a water distribution system, sensors might be monitoring water flow, quality, and pressure throughout the pipe. These measurements are then aggregated and sent to a monitoring data collection point where they are analyzed and forwarded to a control function. The control function is in charge of system state estimation based on the recorded measurements reported by the sensor network. After taking the necessary decisions, different control signals are forwarded to different actuators, for example, a water pump, in order to modify their operation according to the system state reported. Therefore, an attacker able to compromise sensor or perform man-in-the-middle attacks can inject falsified data into this loop and indirectly affect the operation of a process. Various techniques have been shown to detect erroneous sensor data, but discarding them is not an option. Depriving the control function of vital information can lead to wrong estimations and wrong decisions by the control function. In this work, focused on protecting a system against false data injection attacks in sensor networks, we aim to utilize machine learning techniques to create physics-based models. These models, created through data-driven learning techniques, can act as backup system information providers when sensor tampering has been detected. However, CPSs are characterized by complex physical phenomena, typically modeled by means of approximation algorithms, which are very computationally taxing and often not accurate enough. State-of-the-art approaches for securing CPS rely heavily on physics-based models of the physical side. This is why we decided to utilize physics-informed neural networks. An emerging category of neural networks, physics-informed neural networks or PINs, have demonstrated great ability in data-driven training to understand the physical limitations of a given scenario and perform very accurate approximations when regarding physical laws that are described by partial differential equations. This results to fast data-driven inference of partial differential equation solutions. A lot of interesting and computationally complex physical phenomena of interest are described by general time-dependent nonlinear partial differential equations, some of which are liquid flow, liquid contamination, propagation of light in optical fibers, reaction diffusion systems, and many more. These phenomena have exact solutions on paper. However, computers are not very good at differentiation, especially partial differentiation. In order to digitize these calculations, we have to resort to rigorous iterative approximation methods which can be very computationally taxing depending on the solution accuracy required and the scale of the problem. Therefore, it is in our best interests that these physical phenomena are both modeled accurately and require as less as training data as possible. As such, pins are a suitable solution. Pins are simple, deep feed-forward neural networks, deploying hyperbolic tangent activation functions. There is no data regularization required. Pins can create physics-informed surrogate models that are fully differentiable with respect to all input coordinates and free parameters. Using these models, a pin is able to infer solutions to a partial differential equation accurately. Pins are built upon the aforementioned principle of leveraging physics-inspired information about a system and can be trained with low amount of training data. By naturally encoding any underlying physical laws as prior information and/or restrictions, pins are trained to solve supervised learning tasks while respecting any given law of physics described by general nonlinear partial differential equations. By leveraging this physics-influenced knowledge, pins are able to quickly steer towards the correct solution. As a result, pins can work in scenarios where data is scarce, since physical laws amplify the information of the data that the algorithm sees. Our proof of concept scenario consists of an indicative part of a smart water distribution system in which a pump pushes liquid through a pipe and aims to maintain a constant flow by adjusting its operating conditions according to measurements captured by sensors placed in the pipe. In this work, we consider a case of an incompressible fluid flowing past a circular cylinder. We assume a non-dimensional free stream velocity, a cylinder with constant diameter, and that the fluid is uniform in density across the cylindrical channel. Sensors are placed inside the channel and record the fluid's velocity. The sensors report the measurements to a control algorithm in order to take appropriate actions via controllers and actuators for the liquid pump operation. An attacker, aware of this feedback loop, tries to interfere with the reported measurements to indirectly mislead the controller and steer the system towards amplifying the error in the estimation and thereby leading to a non-convergence or even towards a possibly unstable state. This way, the attacker may fool the control function that something has changed and force unexpected changes to the pump's operation. The system, however, experiences no malfunction and every underlying physical or software process is running error-free. A monitoring and detection unit, in short MDU, is in charge of gathering all the measurements recorded by the sensors and placed in the pipe. Assuming the MDU can detect the attacker tampering with the sensors, the erroneous measurements can be singled out and discarded. The MDU will then notify the pin of the compromised sensor and request replacement artificial measurements. Knowing the sensor's spatial coordinates in the pipe, the pin trained to infer the liquid state in the pipe can quickly and accurately create artificial measurements acting as a virtual sensor. These artificial measurements, combined with the unspoiled recordings of the rest of the sensor network, should provide enough information for the control function to correctly produce the appropriate control signals and steer the system towards the next stable state. Completely disregarding the false sensor readings without any action could end up making the system unobservable and in extension affect the control function's ability to estimate the system state correctly. To train the pins on inferring the liquid's velocity, we utilize the two-dimensional form of Navier-Stokes equations. They are considered to be very accurate in describing liquid flow in a pipe, which is a common occurrence in water distribution networks. The trained pin will be able to infer U, V, and P when introduced to spatial and temporal coordinates of the pipe. The pin's training dataset is created with measurements taken by sensors. This way, we can train a pin under the normal conditions of a fluid moving through a pipe at a constant flow and have fast and accurate prediction on the pipe state on every spatial and temporal coordinate. This pin can then be utilized in our proof of concept scenario, which we are going to be explaining next. Now let's take a look at a more complete view of the scenario described. The sensors stationed in selected spatial coordinates throughout the pipe monitor the liquid's U and V velocities periodically. The sensors report the measurements to the control algorithm. The attacker tries to compromise several sensors either by fully compromising a remote wireless sensor or perform man-in-the-middle attacks. This way, the attacker can fool the system into changing its operating conditions unnecessarily by providing bogus information and making the control function think that something is wrong, when in reality everything works fine. Assuming that there is a functioning monitoring and detection unit in place, the erroneous readings from the compromised sensors will be detected. However, completely ignoring these measurements can lead to losing system observability and push the control function to make uninformed decisions, which can cause system failure or malfunction. In order to address the issue of removing the detected and contaminated data and thus keep the system observable, a trained pin can be activated and act as a temporary surrogate data provider to the control function. Therefore, the pin can fill the gap due to discarded sensor measurements since has been trained to model the liquid's flow under normal operating conditions. We can safely rely on a virtual pin-enabled sensor to maintain system observability and continue the normal operation until the attack has been stopped without having to shut down or lose control of the system. So to further explain our experimental setup, we first have to explain how the pin was trained. In order to create a high-resolution dataset, we create a cylindrical channel using Gmesh by creating a rectangular mesh geometry discretizing space in triangles. The discretization of space is carried out for the computational solver of the Navier-Stokes equations included in the Nectar++ framework. In our experimental setup, the pin trained with simulated data was able to accurately predict U and V velocities with 99 and 95% accuracy respectively, using only a small subset of the total training data available. In this paper, we demonstrate the applicability of pin as a mitigation mechanism against observability cyber attacks in CPSs. We show that the pin can be very accurate with minimal training and a small dataset. This way, complex physical processes can be accurately characterized without the computational complexity and effort of traditional approximation methods. However, there is still room for improvement and investigation. For example, we need to verify that the pin can retain its high accuracy through the test of time. We also aim to retrain the pin using datasets derived from digital twin testbeds in the immediate future, to test the hypothesis that pins will still be accurate when trained with real-world and probably noisy data. A few other challenges are still at large, such as the mitigation mechanism of the current work, which assumes a detection mechanism against falsified data. There are some solutions in the literature, but an extensive research on finding the best fit in this scenario is yet to be realized. We also aim to create a new detection unit that may utilize the pin's prediction to detect erroneous data or even categorize anomalies into actual cyber attacks or just malfunctioning sensors. Thank you very much for your attention, and we are looking forward to your questions.
Thank you, Solona, for the presentation.
Looking forward to your questions.
I'll pause it here. So if anybody has any questions, either feel free to unmute yourself or post the questions in the chat. And having said that, there are two questions from the participants. Ioannis Zografopoulos asks, given that physics-informed neural networks are a type of DNNs, it's a type essentially of neural networks, have you studied how your method performs so long against adversarial examples?
So if I understand correctly, can you hear me?
Yes, we can hear you.
Yeah. If I understand correctly, the question here about adversarial examples is forged data that will pass as legitimate and not be detected. If I understood the question correctly, then no, we have not tested that, but it's in our plans for the immediate future.
Okay, thank you. And the second question, how often does your system need to be retrained? Is it necessary to retrain every time that the architecture of the overall system changes? For example, you have new equipment, you have new sensors, you have different placement of the sensors in the system?
So as long as the system stays the same, there is no need to retrain the model, since the flow of liquid in the pipe is going to stay the same. Several factors that may lead to the need to retrain our model is maybe erosion through the pipe, which may alter its dimensions after a long period of time. If we add new sensors or new equipment in the pipe, it is not going to affect the pin, because it is able to extrapolate the results that it creates in all the spatial coordinates in the pipe that it was trained for. So if it is placed between the dimensions that it was trained for, it will be fine for whatever spatial coordinate you are going to choose. But if another sensor is placed in, let's say, out of bounds of the scope of the training used for the pin, then it will need to be retrained.
Okay, thank you. And I have a follow-up there. Can you replace in this system all the sensors with pin-enabled sensors, virtual? So you don't have any sensors if all are compromised. Can you replace all the data you have with this observable virtual data?
So if our goal here is to keep the system running in a stable state at whatever the cost, then it would work. But it is not a recommended practice, because losing the ability to detect faults and attacks when they really happen and when they are not forged data will lead to a state that you cannot see when something was actually broken. So a plausible alternative to full physical sensors or full virtual sensors, I assume is going to be a hybrid approach, but we need to find a good compromise or an optimized balance between physical and virtual sensors, so that you have enough sensors to detect possible faults or actual attacks and changes in the state of the system, and supplementary virtual sensors that are going to enhance your resolution and your visibility to the system. And in order to keep the system visible if some of the physical sensors do break or get compromised. So a full virtual sensor system, in my opinion, would not be practical.
Okay.
This is another approach that we need to take and examine what's the best trade-off between the number of physical and virtual sensors.
Thank you, Solana. I think we're just in time for the Q&A session of this paper. Thank you for your insightful answers and for the interesting presentation. For the next paper, we have a collaborative work from University of Central Florida and University of Florida. And we're gonna hear Feng Wu present their work on resilient distributed estimator with information consensus for cyber-physical system security.
Hello, everyone. I'm gonna present our work today, which is called Resilient Distributed Estimator with Information Consensus for CPS Security. My name is Wang. Our collaborators include Yao Dan, Dr. Tan, and Dr. Ye. I and Dr. Tan, we are from Department of Mathematics, University of Central Florida. Yao Dan and Dr. Ye, they are from Department of Electronical and Computer Engineering, University of Florida. So here, this is our agenda for this talk. So basically we have 5 parts. for this talk. So I'm gonna discuss some of the motivations for our work, and I'm gonna talk about some preliminaries and our method, resilient distributed estimator with information consensus, which I may call this RDAC algorithm. And I also will give one simulations for our work, and I will draw conclusions at the end of this talk. So cyber-physical system experienced rapid developments in recent years due to its advances in computing, communication, and related hardware technologies. However, CPS community has been aware of its vulnerability in front of cyber attack. So one recent example is that the Ruggers a software technology company, successfully spoofed the Tesla Model 3 off the highway in 2019, and made the vehicle turn around on its own. A platoon of connected and autonomous vehicles may have severe incidents caused by cyber attacks. So one of the fundamental solutions is to design a safe and robust estimator for each vehicle. So we modeled the N vehicle platoon by discrete linear time invariant equations. So the state of a platoon is denoted by X, and its evolution is governed by Sk plus 1 equal to AXK. So each vehicle will equip a sensor. The sensor measurement is given by this equation. So we have the YIK equal to CI times K XK. If the sensor is under attack at time K, we're gonna add a attack vector AK to this measurement Y. So here W and V, they are noise. They're noise for the system and the sensors respectively. Our goal is to estimate Sk when the noise WV and the unknown attack vector AK exist. So it's a pretty tough task actually. So to describe a realistic situation, such as the communication failure, we denote the communication graph at time K by GFK. And we also require a pretty weak condition, which is called the jointly strong connectivity. So it means that all vehicles will stay connected during a certain period of time. And one more common assumption for the estimator is that the system pair AC. So AC basically they are the matrices for the system. So we're going to require that little pair AC is observable. It's pretty natural assumptions for the estimator. We also suppose that the attacker cannot attack communication channel. So the information among the vehicles is instant. Vehicles will trust all information from its neighbors. So which means that all these cars will accept both malicious and non-malicious state estimates from its neighbors. Because the noise exists, so common filter is very common to use to estimate the states. And the common filter is recursive and it can be run in real time using only the present input measurement and the previously calculated state estimates. However, a common filter requires a computation center that every sensor needs to send their data to that sensor. This may cause some limitations, such as scalability, communication delay, and limited communication bandwidth. So under these limitations, distributed common filter is introduced to tackle such problems. So the system states can be estimated at each vehicle. And the covariance matrices in distributed manner are shown as here. So the formula PI at K plus 1 here, this is a covariance matrix at K plus 1. And it's equal to the inverse of the sum of these terms, or the sum of these matrices. If the graph is time static, so which means that the graph does not change over time, so it can be proved that this matrices layout converge. So in practical, basically we use the convergent, the limits of these matrices to the estimator. But when a graph is time variant, which means that if the graph is changing over time, so this matrices, the arrow covariance matrices, still can be computed independently. So we're gonna take advantage of this this property. So the updated rules of the distributed common filter are shown here. So x hat here is the estimation of the state vector x. So it can be shown that the distributed common filter is equivalent to a minimization problem, and the objective functions is given by here. So objective function is yi minus cxi squared plus 1 over d times the summation of the xi minus x hat j. So x hat j, you can see that this is a estimation from its neighbors. So this minimization problem use the local information measure yi, and also use the information from its neighbors, xj hat. So the distributed common filter can be viewed as an estimator minimize the loss at ICE vehicle. So if we consider this is the loss, okay. So the loss includes the two parts, local loss and the neighbor's loss. Neighbor's loss measured in so this is the neighbor's loss and this is the local loss. Neighbor's loss measures the influence of the neighbor's estimation, and the local loss measures the innovation at ICE node. So we can observe that the local loss in DKF is quadratic. So it's very sensitive against the sensor attacks. And one common technique is to use the L1 norm for the term affected by attack. So we can see that y is measurement, and it can be manipulated by the attack. Okay, so one common technique is to use the L1 norm for this term. So based on this idea, we propose the two novel different local loss here to obtain a robust data estimator. So the first version of the loss is we still use the square and the quadratic form for the term, but we're gonna abstract the AI. So we're gonna exclude the influence of the vector, and we're gonna add some penalty for the attack vector. So we're gonna use the lambda times the L1 norm of the AI. So in this case, if the attack vectors change pretty large, but still will not influence the objective values a lot. So this loss as well makes the estimator more robust against the attacker. And the second loss, which is pretty similar to the L1 norm, but we're gonna estimate one of this by this term. So you can see that the denominator is pretty close to the y minus cxi because we use the axi hat, the estimation from the previous step to approximate the estimate at this time. So the whole term is equivalent to the one norm of this term. So the second version of the local loss still has the same effect of the L1 norm. So these are two local lessons make the estimator more robust against the attacker. So we consider a consensus problem in distributed manner, in distributed estimate as well. So consensus here means that each local node and its neighbors may reach an agreement. So it's equivalent to see that we're gonna add a constraint then xi equal to the xj for its neighbors for this problem. So along with this constraint, it's very natural to control the total loss of all vehicles. So to solve this problem, we're gonna introduce a copy variable, which I may call it z. So this it can be shown that these two problems are equivalent. And the right-hand side, so this problem can be solved by a technique which is called the alternating direction method of multipliers, ADMM, effectively. So this problem can be solved in several steps. It's pretty effective. So I'm gonna conclude our algorithm update in this pseudocode. So we input a matrix as PM and measurement. So we're gonna update the loss function at each iterate first, then use the ADM solver to finish the inner iteration. Then the result updates the estimation at a time k+1. So we'll compare our method against distributed common filter for a static graph and a time varying graph. So we can see that our DAC has the better performance and it has a smaller error without attack. So this part of time does not have attack. And even under the attack, so from time k equal to 50 to time equal to 80, and our method still has a much smaller error, which means that the method is robust against attack. So decibel 6 means that the error goes up to 1,000, which is not acceptable in real situation. So I'm gonna conclude our method here. So RDAC, we propose RDAC, which is a distributed estimator based on consensus, and which is robust against sensor text. And our method has a better performance in both situations, like both static and time varying communication graphs. Total loss in both situations, like both static and time.
Thank you, Frank. Sorry for this. I couldn't catch the last part of the presentation in order to stop it. Anyway, thank you for the very interesting, although I'm a little bit heavily math work. It's very interesting to see such distributed estimators can be applied in large scale cyber physical systems. I would like to open the floor for any questions. I don't see any questions in the chat. If there are any questions from the participants, as a reminder, you can ask them to the chat or unmute yourself. If not, I can ask a question. So you mentioned about loss functions. So what are the difference between the two different loss functions that you presented?
Hello, can you hear me?
Yes, we can hear you.
Okay, so basically we propose the two versions of the loss functions, local functions, but there is some there has their own like advantage and disadvantages. So the first version of the loss functions. So basically we separate the influence of the attack vector outside the term that that evaluate the local loss. So in that case, we added a lambda, we added a penalty term for the attack vectors. So if we adjust the parameters, so basically we can just control the influence by the attack. But at the same time, we don't affect the convergence rate, the rate of the convergence in this case. But there's no general solutions for that optimization problem. So the disadvantage for the first version loss function is that it may take much more resource or take much more time to compute in practice. So to handle these situations, we propose the second version of the loss functions. So basically, in this case, the whole functions has a very fast solutions. So basically, every step of the convergence can be computed in one step. So, but sometimes if we got a more attack, the attack So the sensor measurement is changed by the attack a lot. So we have to adjust the penalty parameters lambda in that case. But that terms, which if we increase the value for the lambda, so that sometimes will affect the convergence of a rate of the functions. So it may lower the convergence rate in practice. So that's the main difference of these two loss functions.
Okay, so lambda affects the conversions of the estimator. Does it affect something else? The parameter lambda?
Yes, the lambda. So in the first version of the local loss, lambda only affect the attack factor.
Mm-hmm.
So if we adjust the lambda, it doesn't really change the rate of the convergence.
I see.
But the second version of the loss functions, the effect by the attack is like confused combined with the local measurement. So if we adjust the lambda, it may lower the convergence rate in the practice. We made several experiments to see that happen. But
thank you.
But eventually, it's like it faster. We got a better result without attack. That's the trade-off.
I see. So thank you, Feng. Thank you for the very interesting presentation and for answering my questions. With that, I think we should move forward and go to the next presentation. So the next presentation is from Anomadarshi Barua from University of California, Irvine. And he'll talk us about the non-invasive insertion spoofing attacks on embedded and cyber physical systems. And with that, I will mute myself and play his pre-recorded presentation.
Hi everyone, I am Anomadarshi Barua from UC Irvine. I am going to present one of our works on this special session. The name of our work is Non-Invasive Sensor Spoofing Attacks on Embedded and Cyber Physical Systems. Before going to present our main work, I want to give an outline of this presentation upfront. At first, we will give a generalized view of sensor hardware in today's embedded and cyber physical systems. And we will show how vulnerable today's sensors are against external spoofing by an attacker. To support the sensor vulnerability, next we will present a new attack model that can compromise sensors in general. Next, we will use Hall sensor as our case study of sensor spoofing attack, and we will explain the attack tool to compromise a Hall sensor externally. After that, we will validate our attack model experimentally in a test bed. We choose a real power grid as our test bed in the lab setup. Next, we will provide research challenges along this direction. Now we will start by giving the generalized view of sensor hardware in today's embedded and cyber physical systems. At the very beginning, let's give some foundational knowledge on economic growth of sensors in today's market. Sensors are so abundant, prevalent in today's systems. Sensors are everywhere. We can find sensors from IoT to autonomous vehicles, airplanes. It has been estimated that industrial sensor market size is expected to grow from USD 18.2 billion to USD 29 billion by 2025. We all know that sensors are one of the most sophisticated and integral components of embedded cyber physical system. Apart from sensors, embedded and cyber physical systems comprise of different components such as gateways, microcontrollers, different sophisticated operating systems, robust protocols, etc. Tremendous amounts of efforts are given on hardening these protocols, operating systems, gateway nodes, etc. But we are sorry to say that a very little amount of works are done focusing on sensor security. Sensors work as ears and eyes of today's embedded and cyber physical systems. Most of the today's sensors are still vulnerable to external spoofing attack. Therefore, an attacker can use these sensors as entry points to the embedded cyber physical system. In this slide, we will discuss different components of sensor hardware in general. As we can see from this figure is that the main component of a sensor is a sensing structure. For example, a microphone has diaphragm as sensing structure. This sensing structure measures physical quantities and stimulus signals coming from the surrounding environments. This measured signal quantities are then converted into a usable electrical signal that passes through amplifiers, filters, ADCs, and eventually arrives in the main connected systems. It is clear from this discussion that there is no hardware-software firewall present between the sensor and the system interface. Therefore, this could be an entry point by an attacker. A smart attacker can non-invasively inject fake signals into sensors by using a suitable spoofing technique. The injected fake signals can eventually propagate from sensors to the underlying system controller and can cause system failure, resulting in denial of service attacks on connected systems. From the last slide, we come to know that the attacker can compromise the system availability and integrity by attacking just only a single sensor. There are similar attacks in the newspaper. One group of researchers show that a $300 projector can fool Tesla autopilot system. Another work demonstrates that an ultrasound can deliver secret message to Siri. It has been proven that a sonic gun can disturb the operation of man's gyroscope and destabilize drones. Nowadays, more and more attacks are coming on the sensor surface in different applications. This slide tries to give a general impression that lots of demonstrations on sensor spoofing attacks are going on. The attacker can attack an automotive system just by attacking lidars, cameras, radars, etc. by using external spoofing signals such as lights, infrareds, RF waves, etc. Similar types of sensor attacks are also possible on drones, hard disks, medical device industries. This table clearly indicates that all these moderate to severe attacks may happen just by spoofing a single sensor. Therefore, this type of non-invasive sensor spoofing attack is already a concern in the community. This will be more important in the near future when sensors will pervade our lives. So far, we have provided a general overview on attacking sensors using external spoofing signals. Now, we will formalize the attack by introducing our attack model. Now, we discuss the components of the attack model in details. The attacker can inject malicious stimulus signals into sensors. As the injected signal is coming from the physical domain, the sensor spoofing attack can be termed as a physical attack. Though the attack is coming from the physical domain, the attacker is not allowed to invasively access and modify sensor hardware and software. In this sense, the attack model is non-invasive. The attacker could be a disgruntled employee, visitor, or the attack could be an interdiction. Moreover, the attacker can attack the sensor in a stealthy manner. The attacker can camouflage the attack tool with a remote control within a small container. This camouflage attack tool is hard to detect. The attacker can remotely control the camouflage attack tool and wisely choose the timing of the attack to remain unidentified and to maximize the impact. This makes the attack model strong and stealthy. This type of attacks comes from a physical domain and impacts the cyber domain of the connected system. So this attack is a cross-layer attack, and knowledge of different cross-layer attacks are required to identify and nullify this attack. So this type of attack is strong and can impact different embedded cyber physical systems such as autonomous vehicles, smart grids, industrial plants, robotics, etc. Now we use a Hall sensor to demonstrate our attack model as a case study. We are going to attack the Hall sensor present inside of the solar inverter. Hall sensor is an analog sensor which has excellent accuracy, high efficiency, very good linearity, and suitable for simultaneous AC/DC voltage current measurement with galvanic isolation. Therefore, Hall sensors are pervasive in high-power inverter applications. Here is the inside view of 100 kW solar inverter that clearly points the presence of Hall sensors. Before going to demonstrate our attack model on Hall sensor, I want to say something on Hall sensor basics. A Hall sensor comprises a Hall element which is made of a thin piece of p-type semiconductor material. When this Hall element is placed within an applied magnetic field B, because of the Lorentz force, a Hall voltage V Hall will be generated across the Hall element. The equation of V Hall is shown here, and this equation is illustrated by a figure here. This figure shows that the relation between V Hall and B is linear. As V Hall depends on B, by injecting external magnetic field B, the attacker can change V Hall. Now I'm going to explain the attack tool that the attacker might use to attack a Hall sensor using our attack model. The attacker can inject constant sinusoidal and pulsating magnetic fields into a Hall sensor of the inverter by using our attack tool. The cost of this attack tool is approximately $50. The attack tool has an electromagnet, Arduino board, RF modules, and battery packs. The attacker camouflages the attack tool within a small container such as flower vase. Then the attacker can place the camouflaged attack tool near the inverter. The attacker just needs a brief one-time access to the inverter, and it might not be difficult in an isolated solar plant. Now we will validate our attack model in a test bed. A scaled-down version of a power grid is created as a test bed to demonstrate the spoofing attack on Hall sensors. A 40-watt inverter from Texas Instruments with a steel shield is used in the test bed. The inverter has Hall sensors inside. The attack tool is placed 8 cm away from the inverter. Our attack tool can spoof Hall sensors from at most 10 cm distance. The inverter is connected with a solar panel which is emulated by a DC source. A small-scale load is used to model the grid load. Another power inverter is used to emulate a weak grid. There are 3 places in the inverter where the Hall sensor can present. two places near the grid line to measure grid voltage and current, and the other place is near the PV panels. If the attacker attacks the Hall sensor near the PV panels, the attack propagates through the MPPT plug, then goes to the PI controllers, and finally impacts the PWM inverter. This disrupts the inverter voltage and current. If the attacker attacks the Hall grid current sensors, the attack propagates through the ABC to DQ transformation block all the way up to the PWM inverter. If the attacker attacks the Hall voltage sensors, the attack disrupts the PLL block. This disruption hampers the grid synchronization by altering inverter output voltage and frequency. The outcome of the attack is shown in this slide. The inverter voltage goes out of phase after the attack. The inverter frequency also changes, which distorts the wave shape. The left video shows that the output voltage fluctuates, and the right video shows the frequency is disrupted because of the attack. To validate our attack model on large power grid, we have used practical industry software ETAP to demonstrate the attack impact on a large grid. We have modeled a 2.3 megawatt of medium-sized grid using IEEE 13 bus model. The attacker targets a 100 kilowatt inverter of this grid to hamper its normal operation. This figure shows that the attacker attacks the Hall sensor of an inverter at t equal to 2 seconds. After this point, the grid voltage and frequency start continuously decaying and fall to 97% of the rated values within 8 seconds. IEEE 1547 standard indicates that the grid will shut down as the grid frequency is out of the range. This may result in a blackout in the region. Now we are going to provide research challenges along this direction. Any defense methodology which has an intention to work against a sensor spoofing attack must consider the components of the attack model explained in our work. To provide defense against this attack model, we must keep few things in mind. First, security should be considered while designing sensors because sensors and the physical environments around the sensors are not trusted anymore. The next generation defense method should not only detect the sensor spoofing attack but also should contain the attack inside of sensors so that the attack cannot propagate further to the connected systems. Sensors cannot remain naive anymore, and they should be smarter while handling stimulus physical entities from environments. Novel hardware-software architecture should be introduced in the sensor-level design that may act as a firewall in the sensor system interface. For example, the time-sensitive applications of the firewall should be implemented in FPGA to increase the processing efficiency and reduce the deterministic latency. The inclusion of parallelism using analog and digital domain in the sensor-level design will add a new dimension in the next-generation defense. This will help to keep the bandwidth or other normal system performances intact. I'd like to run a video first to demonstrate our attack model on gridded inverter in our lab setup. Here, you can see the basic components that were used in our lab setup to demonstrate our attack model. Before the attack, the inverter output voltage, current, and frequency all stable, as you can see. Now the attacker is going to place a camouflage attack tool near the inverter with remote access. At a remote location, now the attacker activates the attack tool and start injecting magnetic pulses into the inverter. As you can see, the output voltage of the inverter starts fluctuating after the attack. You can see the fluctuation in the oscilloscope also. Thank you for your attention. Please feel free to ask any question.
Thank you, Madarshi, for the nice presentation, for the interesting presentation. Let me take it a little bit back here.
Any question?
Okay. Are there any questions from the participants? please feel free to unmute yourself. I have one quick question. So you presented one attack on the inverter, and you presented also a simulated 13-bus system that you essentially simulated the attack, right? Have you done a combination of those experiments in what we call a hardware in the loop approach? What I'm asking is the simulation is connected with the outside work with the actual inverter, or is it purely emulated within the simulation environment of ETAP?
Thank you for your question. Can you hear me?
Yes, we can hear you.
That's a good question. So hardware in the loop testing is our current work, what we are doing right now. So in this work that I have already shown, where we have used the ETAP just for simulation, we have not connected this simulation with any external world. But in the first demonstration, where in the lab setup, we have used the solar inverter and connected the solar inverter into the actual grid.
Okay, thank you. And another quick question, if nobody has any question, is how much is the distance? So is it possible to attack the whole sensors using magnetic fields? So how much distance is it possible? Yeah.
In this current work, we can spoof the Hall sensor from at most 10 centimeter distance. But if we replace the electromagnet with some rare earth material, for example, the neodymium, then we can actually increase the distance to 15 to 20 centimeter.
Okay, thank you. And the last question is comes from Solon Falas. Is there any way to shield the internals or the coding to protect against this electromagnetic pulses?
Yes, the shielding is one of the defense mechanism to protect the Hall sensor from EMP. But I just want to mention that if you increase the injection power, like if the attacker deliberately increase the EMP power, the shielding can also be compromised. So only shielding is not enough. We need to use some intelligent smart controller on top of the sensor in the sensor hardware domain to nullify the impact of the EMP. So shielding is one of the way, but only the shielding is not enough if the attacker increase the shielding power, if the attacker increase the EMP power.
I see. Thank you, Marta. I think there are some exciting future work in the topic with some cost benefit analysis about the shielding capabilities and how much power is it needed to bypass it. Thank you again. Yes. Thank you again for the interesting talk.
Thank you, Professor Harris. Also.
Yep. And going to the last presentation, actually this one is coming from my group. Actually in a meta experience, you're gonna hear me presenting about our work on harness the power of distributed energy resources for secure communications, electric energy systems. And I mute myself and I project the presentation. Thank you for. This is Charalambos Konstantinou, an assistant professor of electrical computer engineering, and I'm delighted to tell you about our work on harnessing the power of distributed energy resources for secure communications electric energy systems. The other co-authors of this work are Ioannis Zografopoulos and Juan Ospina, and we are part of the Decision and Secure Systems Lab at the Center for Advanced Power Systems, Florida State University. Let me start by saying that electric energy systems are undergoing significant changes to improve system reliability and accommodate increasing power demands. Over the past years, electric energy systems have diverged from a unidirectional generation and transmission model towards a more distributed architecture that supports traditional generation resources as well as distributed generation such as PV and wind, and distributed storage sources such as battery and thermal energy storage systems. This transformation is enabled due to the introduction of information and communication technologies, automated control systems, remote sensing, and embedded IoT devices. However, the information and communication technology devices enabling such cyber-physical energy system transformation expand the threat surface of the energy infrastructure. The vulnerabilities within such devices can be ported to the industrial environment, creating potential entry points for malicious adversaries that focus on disrupting cyber-physical energy system operations. Among several security concerns are ones that relate with insecure communication protocols, improper in terms of bugs and vulnerabilities implementation of protocols, the constraints related to the economic cost and feasibility of updating and upgrading existing power grid equipment, as well as the devastating consequences an attack would have on the electric energy system from generation to end consumers. In this talk, our focus is how to enhance the security of the cyber-physical energy system infrastructure by presenting a solution as a bolt-on security extension that can be implemented on existing industrial communication protocols. The application focus for our security framework is on distributed energy resources. As the electric power grid advances towards a decentralized architecture, distributed energy resources, or DERs, are becoming more prevalent all over the globe. According to North American Electric Reliability Corporation, a DER is any resource on the distribution system generating electricity. Examples include PV systems, electric vehicles, wind turbines, which are often bolstered by energy storage solutions such as battery energy storage systems, fuel cells, and flywheels. DER generation capacity is expected to reach 530 gigawatts by 2026. Despite the various benefits of DERs, including optimization of power grid resources and bidirectional energy flow, existing communication standards and protocols between DERs and grid utilities or aggregators, lack of cybersecurity standards, can be outdated or insecure, and embedded devices supporting such communications, despite being resource constrained in terms of computing resources, can be maliciously attacked by adversaries. In terms of DER communication protocols, an overview of the existing DER protocols along with their encryption authentication requirements, type of information, type of transmitted data, etc. are shown in this slide. Although new protocols such as IEEE 2030.5 feature cryptographically secure and authentication properties, there is a plethora of already deployed grid devices utilizing insecure or outdated communication protocol versions. For example, more than 75 of North American utilities employ IEEE 1815 Distributed Network Protocol or DNP3 for supervisory control and data acquisition. DNP3 vulnerabilities undermine not only the security of the communication channel, but also the security of devices relying on this protocol. Recently, DNP3 received updates to conform with interconnection interoperability standards such as IEEE 1547/2020 and features security properties similar to newer protocols. However, the protocol has still significant drawbacks and legacy devices still remain a valid concern. As with most cybersecurity problems, there is no single silver bullet which can address all attacks. In this work, we provide a security extension that can enhance utility to DER communications while requiring minimum redesign efforts. We aim to improve the communication security of DER interconnected systems from the lowest level of abstraction. Specifically, we leverage the inherent cell entropy from battery energy storage system enabled DER devices to develop a security primitive which can be incorporated in DER communications and support secure authentication. Our framework, named DER Auth, secures the measurement and control command data issued to DERs. It provides a security extension that can be retrofitted to any battery storage enabled grid asset which uses DNP3 with minimum redesign requirements, serving as an authentication layer on top of the DNP3 protocol stack. A high-level overview of DER framework is presented in this figure. It operates using a challenge-reply scheme between the DNP3 master and the DNP3 outstation devices which are located on the DER side. It requires DER outstation devices to be authenticated before control commands can be issued from the DNP3 master. The authentication process leverages the intrinsic characteristics of the battery energy storage system lithium-ion battery cells to generate entropy, and specifically cell voltage and state of charge measurements and their inherent randomness caused by the unique lithium-ion physical properties due to their manufacturing process. To summarize, we developed and ported a battery storage-based authentication scheme into the DNP3 protocol stack. We utilize lithium-ion battery measurements factoring the real-world discrepancies for the secure authentication process, and we provided the implementation details of the design, which can be ported in any DNP3 assisted industrial control environment, reinforcing communication security. In order to evaluate DER auth, we have developed a proof of concept implementation in which lithium-ion battery cells are used as the battery energy storage system of DERs. The setup provides the state of charge and voltage measurements of cells with a maximum error of ±1%. To attain the highest possible accuracy, each battery cell is subjected to a learning cycle. The cycle involves a full discharge for the fuel gauge module to accurately calculate each cell's impedance. The setup is presented in the upper left figure of this slide. Besides the voltage and state of charge discrepancies between identical lithium-ion cells as the number of cycles and ages increases, the relationship between state of charge and voltage values is also non-deterministic, as presented in the bottom left figure of this slide. In our design, the multiple lithium-ion cells constituting the battery energy storage system of the DER are leveraged towards entropy generation. In other words, the voltage and the state of charge of each battery cell are utilized towards the development of DER auth. For the evaluation of DER authentication process, we implement a testbed setup where two computing stations communicate via DNP3 as master and out station. The right figure of the slide depicts the overall top-level diagram of the test setup. The master and out station devices are running modified versions of DNP3 using the open source OpenDNP3 library, which is an open source reference implementation for the DNP3 protocol. We have extended OpenDNP3 to integrate the DER auth challenge reply mechanism and support an SQLite database to store the temporally challenge reply values exchanged during authentication. In this implementation, the DNP3 outstation is modeled as an agent that interacts with the battery energy storage system, in other words, the DER, and the master DNP3 device is modeled as an agent that sends the corresponding charge-discharge set points to the outstation distributed energy resource. Experimental results implemented on the OpenDNP3 stack validate our scheme using battery data generated by lithium-ion cells. To assess the operation of DER auth within the test setup presented in the previous slide, a modified version of OpenDNP3 integrating DER auth is deployed in two different computers connected via an Ethernet switch. The DNP3 communication protocol runs over TCP/IP, and the master and outstation are configured to interchange 64-bit float analog values. In this case study, the master device initiates the DER auth authentication process every time it sends a new setpoint command to the outstation controlling the DER. Specifically, in our scenario, the DER auth authentication challenge is predefined to occur 5 seconds before the master sends the corresponding operation command to the respective outstation. Although a 5-second interval is selected for this case study, any other value could also be used depending on the operational requirements. The figures in this slide present the voltage and state of charge measurements from the two cells used in DER auth. The total simulation time is 5,000 seconds, and 4 battery operations are requested by the master controller. These operations are a 10-watt discharge request at 500 seconds, a no operation request at 2,000 seconds, a 10-watt charge request at 3,000 seconds, and finally a no operation request at 4,500 seconds. At each of these points, DER auth is executed before 5 seconds the setpoint command is issued. I would like to conclude by saying that the takeaway point of this presentation is that security in modern cyber-physical systems is a major concern. The communication protocols employed for DER management and control in electric energy systems lack sophisticated cybersecurity features and can compromise power system secure operation if malicious control commands are issued to distributed energy resources. To overcome authentication-related protocol issues, we presented a security extension that can be implemented on DNP3 protocol. That brings me to the end of my presentation. You can find more information of our work as well as contact details on our lab website shown in this slide. Thank you for your attention and thank you for listening. Okay, I think with that presentation, we're at the end of this session. Any questions from the participants about our work? Ioannis, PhD student, is here as well to answer any questions. Any questions? I think there is one question in the chat. So is this open source? If not, is there any planned release or do you have plans to make it open source? Yannis?
Hello.
Yes, we can
yes,
hear
I
you.
can hear you. Yeah. Hello, Solon. Thank you for your question. Yes, so actually at the moment we are working on fine-tuning our code. We plan to release it along with the report on the whole system, how it is going to be working and actually how you can reconfigure it based on your operational constraints, how often you need to authenticate things, how sensitive it is going to be, how often you're going to take measurements. So we plan on releasing all those things with information on how to set it up. So watch this space and yeah, you will see in our future work the code being open sourced.
Thank you, Yanni. And I think one last question, and I think we're at the end of this, we're a little bit over the allocated time. So Dimitris asked if this approach is applicable to any other battery-based systems besides lithium-ion batteries.
Yeah. So thank you, Dimitris. Excellent question. As a matter of fact, lithium-ion batteries are the most difficult chemistry to apply our authentication feature, our authentication scheme. And this is because they have a very stable discharge chart. So their entropy is also limited by this thing. Using a different type of battery, our feature will also work and actually work even better. But given that lithium-ion batteries are the most economical from a power to cost base thing, and they are widely used for storing energy, this was the most prominent battery chemistry to rely on and develop our scheme on.
Thank you, Yanni. Thank you. I think with that, we are at the end of the special session. I would like to thank all the presenters first, being here on a Sunday to present their work and answer any questions. And of course, all the participants. Hopefully COVID goes quickly and we can all meet in the near future together physically. Kuchi?
Sure. Yeah. Thanks, everybody. Yeah. And this is a fantastic session. So we have recordings, and later, if you guys are interested, or these presentations, you can still find it online. Thank you again for contributing to the conference presentation and organizing the special session. This is great. So we are going to end this session. Just a reminder that we have also another session running for the tutorial. If you're interested in open source AI acceleration libraries and compilers, please attend the other one as well. Thanks, everybody, and have a great Sunday.
Thank you, everyone.
Thank you.
Thank you.
Bye-bye.
Bye-bye.